introduction, Iman. As Iman said, this work is based basically based on my PhD thesis, and the title says it all. It's basically a journey through network control that communicate over a specific wireless network, which is called WirelessHART, and I'm going to try to provide theoretical results for this specific problem. So this work has been done in collaboration with Dragan Nesic and Peter Dawa, both from the University of Melbourne, and also with Roman Postoyan from University of Lorraine in France. Um, so I'm going to start a bit with some motivation. Um, my talk is mostly based in NCS, but tailored to industrial control. So we would have a controller that communicate with the plant over a network. And this type of systems have been used a lot in industrial control lately. So for instance, in electricity, water, oil, and gas distribution systems. They have a big advantage, which is that they provide new applications such as alarming, control, and diagnosis via smart field devices. So these have new capabilities that wired systems did not have before. And the advantage of NCS is that they can adapt all these capabilities to the existing system infrastructure without the need of changing too many things. Now, there's been a trend towards wireless in industrial control, and it has increased significantly, leading to the systems to receive a lot of attention in academia as well. So not only studies presenting experimental results, but also a lot of theory developed for industrial control systems communicating over wireless networks. Why? Because these field devices or smart field devices, they provide simple and reliable points of measurements and control where wires or sensors that were wired could not be placed before. So there's no wiring cost. And more importantly, in many cases, there's no need to change the existing system, right? So I will explain this later on, but these two communication networks that have been specifically designed for industrial automation systems, which are WirelessHART and ISA. But in this talk, at least in my PhD thesis and this talk as well, we will restrict our attention to WirelessHART, but we believe that a similar framework could be adopted to analyze different networks as well. So I'm just going to provide now a couple of examples in where WirelessHART is being used currently in real industries. So the first thing I want to say is that WirelessHART is a multi-hop wireless network, meaning there's multiple field devices lying around and communicating to each other. And these two examples I've extracted from their webpage is MOL in Hungary and Nucor Steel in USA. They've reported savings of up to 50 and 80% in comparison to their previous wired solution, and only with a few routers, right? So they don't need, so let's say if you have a sensor plate somewhere and you want to reach the gateway or the controller, you don't need many routers in between to do that in order to have this good performance. And they've also reported increased blind profit. So I believe, at least when I started my PhD, this is an interesting network that needed more attention. And I'm going to present what's the problem formulation for this. So the way we study these systems is by emulation. So what we do is we forget about the network for a bit, and we say, okay, let's design a controller that's going to stabilize this plant in some sense. And actually, this framework fits somewhat naturally in industrial control because the system was already working with some controller, right? They have, let's say, a wired solution, an already working controller. And what we want to say is maybe we want to now implement everything over a network. We want to communicate everything over a network, but we do not want to change the existing system. We don't want to change the controller. So this framework fits that perfectly. Why? because we would design a controller which stabilizes the plant, and you can use any classical control design. It can come from any nonlinear design or even linear design, whatever you want. But in this talk, I'm going to focus on nonlinear systems. Then the second step is, let's now use the same controller, but now everything is being communicated via this network, in my case, a WirelessHART network. And now the controller does not receive the perfect measurement of the plant anymore, but receives some network version called Y hat, similar for the actuation signal. And now what we're going to do is, can this same controller preserve the initial stability property if we enforce some conditions on this network, right? Often we will provide conditions on how fast you need to transmit, or maybe now we will include the probability of dropouts and things like that. But basically conditions on this network such that the initial controller that was designed without taking into account the network can still preserve stability. So that's the formulation. So as I mentioned, it's been a lot of theoretical work in academia actually focused on wireless HART networks, particularly network control systems that communicate over wireless HART. I'm just listing here some authors, but there's many others that have been working recently as well in this type of problems. And basically they've dealt with linear systems and also discrete time systems. So my idea was try to go up an extra step and try to generalize this a bit into a nonlinear framework and also a hybrid framework. Because when you consider discrete time systems, you are naturally, I mean, implicitly assuming that all transmissions occur equidistantly, and you're only looking at the transmission, the behavior that's capturing at the transmission, but you're not capturing what's happening in between. That's what we want to provide a bit more general framework. So there exist already nonlinear hybrid frameworks that could be potentially applied to our setting. However, I will show that this become really conservative later on. I've listed on the right two seminal papers on this area from Dragon and Andy Thiel and Tabara as well. So they deal with networks of this way. So they have a plant, nonlinear plant, and nonlinear controller, and the output measurement or the actuation signal is sampled and then goes into a zero order hole-like mechanism to make it continuous again. And they study scheduling of data, they study sometimes packet dropouts and things like that. But this is basically a single hop network. So if you were to try to adapt these results into wireless HART scenario in which you have different structure, which is the multi-hop structure, you will get more conservative results. So that's why we need an appropriate framework that is tailored to this specific network and can capture and hopefully exploit that structure. So the outline of my talk is simple. We would have, I'm going to present modeling first. I'm going to try to capture all the features, or at least the more important features of the network into a hybrid nonlinear model. And then we are going to use this model to provide stability results. Then we're going to illustrate these results with some numerical examples before wrapping up with conclusions and future directions. So let's jump on into modeling. I'm going to be looking at all the layers of this network, or at least the most important things that we want to capture. The first important aspect is the architecture of the network. So in this figure, we can see that there is a plant, a controller, and field devices lied around. And field devices are basically what communicate with the plant process. So they could be sensors, actuators, they can also be routers. There's also handheld devices, which are the ones that run diagnosis, but they're not going to be included in my model. And gateways that are the device that enables the communication between the controller and the field devices. you could place it at the controller. You could consider it as an extra node. So there's many ways of modeling the gateway. And the most important part of this network after field devices is the network manager, because it's the one in charge of scheduling all the communications in the network and configures all that is to configure in the networks as well. Now, the three features of this network is that first, they have multi-hop structure, and all the communications happen in a communication frame that is contained with slots, time slots, which I'll explain next. And then you also have different frequencies available to schedule the transmissions. So all these three main features I want to capture in my model. So let's jump onto the communication frame now. As I said, you would have 15 channels. So you have here channel 1, channel 2, and then so on until channel 15. And then the network manager is in charge of defining the communication frame, which in WirelessHART is called superframe, which is composed of different time slots. So all these boxes are time slots. Each time slot is 10 milliseconds long. And within the time slot, there is one transmission happening. So in each time slot, you can only schedule one transmission between field devices. So to illustrate a bit that within this time slot, you would have some synchronization, then this transmission delay, and then some acknowledgement time. So for simplicity, we start making some assumptions in which we assume there's no transmission delay. So we assume that TI will be the transmission instant. We also neglect the acknowledgement time with respect to the time slot length. And we assume that if I have a transmission happening or scheduled in this time slot, and then another one scheduled in the second channel at the same time slot, we assume that they are synchronized. So this assumption, it can be strong, but at least in WirelessHART, there's a strict synchronization protocol. But the future work needs to relax these assumptions so you can have maybe different clocks for each channel. So let's look at transmission instance now. Because of all this synchronization, acknowledgement, all these things that happen within the time slot, most likely your transmission instant is stochastic and time varying, meaning I'm going to schedule a transmission in that box, but I don't know exactly when it's happening. So we will model them. You can model them in two ways. You can consider they're stochastic, and we will use a Poisson point process to count the number of transmissions. And as a consequence, the difference between two successive transmission instants is equal to some tau that's exponentially distributed with parameter omega. This omega is what we call the frequency of transmission. And if you wanted to model these things deterministically, meaning, okay, they could be time varying, they could be stochastic, but I don't care about them explicitly. I'm just going to upper bound them by a tau, a fixed finite number tau, which it's called in the literature the maximum allowable transmission interval. So there's two options. You either model them explicitly as some stochastic process, or you upper bound them by tau, and then your model will be parameterized by this object, and then you establish conditions on this thing. So it'll become clear later on. But so far, you can do these two options. Now we move on to field devices. So in this picture, I've written down specifically that we have field devices on the measurement path and also field devices on the actuation path. And I'm kind of considering a line topology here, but you could consider other topologies, although we haven't done that carefully yet. And field devices, from the specification of the WirelessHART booklet, they should act as a buffer for data that comes from and to neighboring devices. And examples of these are smart sensors, actuators, as I said before, routers, and they usually measure temperature, pressure, flow, and things like that. Now, how do we model this? Because we're trying to deal with a hybrid, we're trying to obtain a hybrid model at the end, we will use that framework to model these devices. So the first thing I want to say is in WirelessHART, these devices are called simplex, so they cannot transmit and receive at the same time. We will define a buffer state variable for each one of these devices. And this TI plus basically means the immediate time after the transmission. So what we say is if this device is receiving a packet, what it does is his buffer value gets updated by whatever is on its input, so whatever is being transmitted through that input. And then because it cannot receive and transmit at the same time, the output remains unchanged. So it's not transmitting anything. Now, what happens when I'm transmitting my buffer state? What I do is whatever's on my buffer, I send it through the output. And because I cannot receive at the same time, my buffer state remains unchanged. So that's what happens at transmissions, but we will also say that in between transmissions, so for any t in this interval, you use like a zero order hold like processing. So you hold whatever's on your buffer state. Now, we introduced a change of variable, which is really useful for modeling and also analysis, which is the network-induced error. So we would define an error for the measurement path and also for the actuation path. And we can see that here there's a lot of differences between signals. And in fact, this is just buffer update during receptions, because let's say if this component is equal to 0, it means that that buffer state is being updated by this input signal. So I'm receiving and updating that buffer. And whenever I'm transmitting, one of these guys is going to be equal to 0. So for instance, if this guy is equal to 0, it means I'm transmitting the content of that buffer state through a signal U2. So we will be setting to 0 components of the error vector according to transmissions. Okay, so that's quite important in our model. Now, scheduling. So far I've talked about transmissions, but I haven't said who is scheduling these transmissions or how do we do it. So WirelessHART specifically can be configured in two ways. You could use a TDMA schedule or CSMA. So on the left here, we have TDMA, which is basically like a deterministic schedule in which the network manager would assign each transmission into the slots I've showed before. And then unless you have packet loss, this thing is deterministic, right? Or if you have stochastic transmission intervals and things like that. But the protocol itself is deterministic, since the network manager is the one that assigns the transmission into the time slot. Now, on the other hand, CSMA, CA, you have all these field devices will compete for access, but only one is successful. So they want to access the time slot that before was given by the network manager. Now all of them are competing, and only one is successful with certain probability. In the literature, this protocol is often called stochastic protocol, and you can also include packet losses in here. So in this talk, I'm going to provide models for all of these situations, but the theoretical results are only going to be presented for the stochastic protocol or CSMA. So in my thesis, you could find all the other theoretical results as well. Now let's start with TDMA with no packet loss. So O here is deterministic. We will define an overall network-induced error, so the measurement error and actuation error in one vector. And we introduce what's called the protocol equation. So here, basically it says what happens to the error right after the transmission instant TI. And that's basically governed by a matrix times the zeta. So H is basically the one in charge setting these error components to 0, as I said before. So let's say I have a transmission at certain time instant. H is in charge to make that component equal to 0 corresponding to that transmission. So because it's TDMA, the network manager is in charge of assigning transmissions. He could pick any protocol he wants. And for any any protocol you give me, I can give you the corresponding H that's constructed based on that protocol. So for instance, if you want to transmit things in a round robin fashion, meaning let's say at transmission 1, you would sample the plant's output measurement, transmission 2, you send that content to field device 2, and then at transmission instant T3, you would send that to field device 3, and so on. So this table would give you a value of H, okay? Now, what happens if we introduce packet loss? So the most simple model for a packet loss channel could be a Bernoulli random variable process. So if theta is equal to 1, then we say that the packet successfully transmitted. If theta is equal to 0, we say it's lost. And how do we incorporate this into our protocol equation? Well, it can be done this way. So H, it's still the same. So it's given by the protocol. And then let's say if transmission is successful, so theta is equal to 1, then we proceed as if this was the ideal case. If it's lost, then theta remains unchanged. And why? Because this hasn't been any update. So I transmitted the packet, but nothing's been updated because it wasn't received. That's why the error remains unchanged, and you can model the whole protocol equation like this. Now, on the other hand, we have CSMA. So to model CSMA, we know that all the field devices are competing to gain access to time slot, but only one of them will succeed. So now the protocol equation has a similar form, but H now is not deterministic because it's not given by the network manager. Now H is stochastic. So it's an ID random matrix that takes values on a finite set. And this set is this. So basically, this set contains all the possibilities of field devices transmitting. So M0 actually is in case you get a packet loss. So if HI takes value M0, means there's a packet loss. If HI took the value M1, it means that field device 1 sampled the measurement of the plant. If takes the value M2, it means there's a transmission between field device 1 and field device 2, and so on. So all this set is basically all the possibilities of transmission. Now, for each transmission, if you have a successful transmission, then HI is equal to some MJ. So some of the field devices has transmitted. If it's lost, then you're equal to M0 or the identity. We also assume that the probability of the HA is equal to MJ is this one, meaning all the field devices have the same chance to access to the time slot, basically. So we're not favoring any field device. They all have the same chance, and there's a probability of loss or transmission, successful transmission, which is equal to P. So therefore, the probability of dropout, or HI, being equal to M0, or the identity, is equal to 1 minus P. So as a summary, you have a bunch of field devices competing, and one of them will access the time slot with some probability. So here I present all the models. So on the left here, we have the TDA model with perfect communication. So X is the augmented state. It contains the state of the plant and the state of the controller. And F is a function of the state, network error, and external disturbance. And here are the network error dynamics as well. And then you have the jump dynamics. So here's the protocol equation. We know that HI is deterministic for TDMA. And because we're in a deterministic setting, the transmission instants are upper bounded by MATI, and they're always successful. Now, if we include packet loss, we saw that the protocol equation changes, and we have this theta, which governs the packet loss. H still deterministic, but now we can include stochastic transmissions and dropouts as well. Now in CSMA, same form for the protocol equation, but now H is stochastic. Remember, there's a probability for these guys to access the time slot. Because it's stochastic setting, we can also include stochastic transmissions and dropouts. So these are the three models, but I'm going to present results only for the CSMA model. Now, important comments on this model is that as opposed to linear and discrete time models, they can cover nonlinear plant controller and the dynamics of all these things, not only at transmissions, but also between transmissions. And the structure of the multi-hop network is reflected in the dynamics of the error zeta. So I didn't write it explicitly, but in fact, you can write the error dynamics as this if you find G explicitly given the system. And this is a non-zero component of the error dynamics. And then this has finite dimension, so it doesn't grow with the number of field devices, but these zeros do. So the larger the amount of field devices, the larger the size of this vector, but in fact, it's because of these zeros increase and increase. So I'm going to show that later, illustrate that. If you treat the vector as G without considering what's actually inside G, if you have a really large number of field devices, you can get really conservative results. But if you exploit these zeros inside, you exploit the structure of the network, then you can get really good results. So these models are also general or generic so that you can use them for different purposes. So tracking server design or the problems. So let's move on to stability results. And before that, I'm going to present some definitions. So if I'm just saying that these results are for the stochastic protocol. So recall this protocol equation in which H is a stochastic matrix that takes values on this set. We define the cover time. So cover times are basically the minimum time it takes to cover all the possibilities. So in another way, if I have field devices trying to transmit, what's the minimum time in which all of them will transmit at least once? Okay, so this is like the stochastic analog of the notion of persistently exciting protocol, which is that. So I need all my field devices to transmit at least once eventually. So that allows us to define the notion of almost surely covering protocol, meaning that a protocol will be AS covering if the probability of this time to being finite is equal to 1. So that's what we want. We want a protocol in which all the field devices have transmitted at some point, at least once. So this is it's not really hard to enforce. Now, our results actually rely on 3 of these assumptions. And first thing I want to say is we treat this system as an interconnected system between plant controller, which is in the X system, and then the network error system, right? So they're both interconnected. And the way if you remember, we're dealing with emulation. So we're saying there was a controller that stabilized the plant. Now we're doing everything through a network, and we want to establish conditions on that network such that the overall network control system remains stable in some sense. So this is the way to do it, and we will use small gain theorem. So we need the protocol to be covering, so we need all the field devices to have access to the time slots at least once in a finite time. And we assume that the error dynamics, network error dynamics, have some exponential growth. The norm here, note that is not the usual norm, since A is the matrix. This is a component-wise norm, and A has this structure. If you remember, the zeta dynamics had a bunch of zeros, so that's reflected in this A. L11 and L12 are just non-zero components that there's no point on specifying here. And we also need that the X dynamics are robust in some sense to its inputs. So we need this guy to be robust. We need the protocol to be covering. And then we will show that this system is LP stable from Y tilde to zeta. And then with that, you can show that using the small gain theorem that the whole thing is stable. So that's the idea behind the proof. And the stability theorem looks like this. I tried to make it as simple as possible without including all the ugly expressions, but basically what it says is if you can find a frequency of transmission. So sorry, let me specify. So this gamma x is the gain of the X subsystem, and this is the LP gain of the error system, and this is basically a small gain condition. Now, this gamma zeta, you can find it explicitly, and it actually depends on omega, which is the frequency of transmission, the number of field devices, probability of successful transmission, L11, which was part of the matrix A as well. So this captures like the structure of the network. And for some problems, you can find explicit expressions for omega, but in this specific problem, it's not easy, and you get like a inequality here that you need to solve numerically. So that's the only downfall. So with this, you will find a bound on omega that depends on all these parameters. If you satisfy this bound, meaning if you transmit fast enough in a way, then you can ensure some LP stability of the system in the sense of expectation, or LP mean stability, often called as well, from the disturbance to the states. From here, you can conclude different types of stability as well, asymptotic stability and things like that, but they're not included here for simplicity. And as I said, you can find the required frequency of transmission numerically. And this theorem basically says that as long as you have AS covering protocol and you transmit fast enough, then you can obtain stability. So if you remember, the initial problem was I already have a controller, and now I want to install a network, let's say, on my industrial control system. You don't need to change the controller. You just configure your network in such a way that the transmissions are fast enough and your protocol is AS covering, and then you're good. So that's a simple way of describing this theorem. And the interesting part is that this bound on omega depends on the number of field devices, multi-hop structure through this L11, and the probability of successful transmission. Now, let's jump into an example. Let's consider a simple nonlinear plant, controller, and also WirelessHART network with 2 field devices on the measurement path, but no field devices on the actuation path. So there's like a wire or something, right? Just to make it simple. Now, if you remember, this tau I was the difference between 2 successive transmission intervals, and it was exponentially distributed. So its expectation is equal to 1 over omega. And this is what we call the average MATI. So it makes sense that because our time instants are stochastic, but I know it's going to happen within the time slot, if my network transmits in average, let's say every X milliseconds, then I know I'm okay. So that's the type of results we want to present. So this table presents different successful probabilities. The bound that you can find numerically using our theorem, and then 1 over this, which is in milliseconds, is like the average MATI. And then you have results from Tabara that could be applicable to our setting, but can get conservative, as you can see on this table. So this theorem, I forgot to say, our theorem is a sufficient condition. So it says if you transmit fast enough, then you can preserve stability. But if you don't know what's happening. So this theorem says if you need to transmit even more fast than this in our case. So it's more conservative, and in fact, it's more clear in this picture. So I've plotted the frequency of transmission on the y-axis, and on the x-axis have the probability of successful transmission. There's some nice intuition here. So first thing you could say is if you have a really poor channel, let's say you drop packets a lot, then intuitively you know you need to transmit fast in order to keep up with the dynamics. If you keep losing packets, then you're not going to preserve stability unless you transmit really fast to compensate for it. So that's intuitively right, and you can prove it using our theorem. So that's cool. And then transmission bounds are less conservative than the ones in the literature. So for this particular example, it's only a 6% improvement, but you can actually show that this grows with the number of field devices. And this actually makes sense because if you remember that G vector, let me write here, that G that contain a lot of zeros here. If you G bar, if you treat this whole thing as G and you have growing field devices, this thing keeps growing and then your results gets conservative. But if you exploit the structure, your results actually will depend mostly on this guy, which does not change dimension. So it makes sense that the improvement grows with the number of field devices. Okay, so as conclusions, we've presented a nonlinear habit framework for the study of network control systems that communicate over a specific wireless network, so WirelessHART, and we've tried to capture most features of that network in our models. As a consequence, we provide less conservative bounds by exploiting the network structure and carefully modeling what's happening in the network. The good thing is these models are generic and we've actually used them for different scenarios, such as observer design. You can also use it to treat different networks, like not only WirelessHART, but different types of networks and topologies. So for instance, similar frameworks have been used to study FlexRay in the past as well, which is another type of network. So there's actually a couple interesting future directions. So one of them is observer design with the stochastic protocol I've just presented. So we've done observer design, but for the deterministic setup, but not for the stochastic setup. And also power control has been a real interest. In fact, imagine now you have multiple wireless channels and each one can drop packets with different probabilities. And you have what's called interference as well if you have channels communicating at the same time. And you also have another guy that comes into play, which is the transmitter power. So if you adjust this transmitter power, you can adjust the probability of successful transmission. That actually generates interesting trade-offs for the overall stability, because if you remember our plot, actually, if you have a poor channel, you need really high frequency of transmission. But what if your network is not, it cannot be feasible. You cannot actually implement that rate of transmission. Then you could play with this transmitter power and make it better. So there's a lot of interesting trade-offs in this area and some preliminary results we've submitted to CDC this year. Another option is to try and co-design optimally the transmission rate and transmitter power as well. That's another open problem we haven't done yet. So I've tried to present the talk as simple as possible to give an overview of some of the results of my thesis. And if you want to look at more detail, you can see these references here, which contain more details. So that's the end of my talk. Thank you very much. And if there's any questions, I'm happy to answer.
Thank you very much, Alejandro. Do we have any questions for Alejandro? Okay, Daniel, do you want to ask a question? Dan?
Oh, hey, sorry, I couldn't find my mic button.
Oh.
Alejandro,
Yep.
if I remember right, your stability theorem was in expectation. Is that correct?
Yeah.
So what exactly does it mean for a system to be stable in expectation? And is it possible for a particular trajectory to be unstable?
So yeah, so basically this type of stability means that in average, let's say, you will behave like this. So if you have multiple realizations, then your state will be fine in average. So, but we don't know anything about, let's say, variance or things like that. It's only in mean.
So if you're implementing something, does this give you confidence in practice that does it mean only half the time you'll be okay? Or what does it really mean?
It's not half the time, but it's stochastic, right? So I think you cannot say anything for sure, but yeah.
Right, okay.
So you could have like one realization where it doesn't work properly, I guess. Yeah.
Cool.
It's not like mean square stability where you know the mean and the variance both converge, right? This is like the mean of the state, the norm of the state. So yeah, it's not that strong, I guess.
Thank you.
Okay, any other questions? Okay, if there is no any other question, let's thank Alejandro again for his talk. See you next week. Thank you very much.